Well, hello, pre-calculus students, seekers of truth especially. We continue our study of the principle of mathematical induction, or PMI, using an example here with the sum of even integers. So what if we added 2 plus 4 plus 6 plus 8 all the way up to some value 2n? Right. So, and notice that this is really 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4, right? So n here, all of these numbers here are what we're representing by n, okay? So n is not 2, 4, 6, 8. N is actually 1, 2, 3, 4. And we're representing the even integers using the value of n. So this is like saying if I were to add up these integers, they would be equal to taking the value of n, squaring it, and adding it to itself. Okay. So let us begin with proving this using the base case, or the base step. This is the most simple scenario when n is equal to 1. So if n is equal to 1, on the left-hand side of the equation, you have 2 times 1, which is equal to 2. On the right-hand side of the formula, you have 2 squared. No, I'm sorry, not 2 squared. See, I messed it up again. It's n that we're using here. So in this case, n is 1. 1 squared plus 1, which in fact is equal to 2. Okay? So the left-hand side does equal the right-hand side. We have proven the base scenario, the most simple case of this. Now let's get to the inductive step. Well, again, we want to assume that the formula is true for n equals k, and then show that it's true for n equals k plus 1. And if we're looking at the left-hand side, it's going to be 2 times 1 plus 2 times 2 plus 2 times 3, and so on, all the way up to 2 times k, and then going one more step, 2 times quantity k plus 1. Okay? And we want to show that it is true, or it's equal to k plus 1 squared plus k plus 1. Okay? So this is what we're trying, this is the assumption that we're making, that the statement is true for n equals k, and we want to show that the left-hand side, when we add this all up, all these numbers all the way up to k plus 1, that it will equal to the formula with k plus 1 substituted in for n. Okay? And to show this, remember, we are always relying on the inductive step, or the inductive assumption. So we want to use the inductive assumption, which says that this statement must be true for everything up to k. So if this statement is true for every statement up to k, then all of this here should be equal to k squared plus k. Now we just add on this extra part, right? If we continue on to k plus 1, adding the next term to this, k plus 1, we want to show that this left-hand side will ultimately be equal to the right-hand side. And you can see here that it is hopefully not too difficult to prove here. Okay. All right. Now from this step, we can do a little bit of, I guess maybe it's easiest just for us to multiply everything out. So we're going to get k squared plus k plus 2k plus 2. And then we can merge all of this together and just kind of like simplify everything by combining all the like terms. So that's k squared plus 3k plus 2. Okay. Now you see, this doesn't quite look like the right-hand side, at least not yet. At least it's not clear that it looks like that yet. So we can take the right-hand side and we can work on it a little bit as well. So we were to take this k plus 1 and distribute it, we would get k squared plus 2k plus 1, and then we would also have plus k plus 1. Combining all the like terms here, you get k squared plus 3k plus 2. And so there you have it. The left-hand side and the right-hand side is in fact equal to each other. So we know that this statement must absolutely be true for all values of k, starting from 1 onward to infinity.